it will be just office hours. Okay, and it's like discussions are not mandatory, it's optional, and the TA again would be doing a screencast of his screen, and he will be like sharing the videos, the discussion videos online, okay, on the course web page. And the readings that we post on the course web page for each and every day, usually, like both Professor Ramzi and I feel that it is better to read it like after class, but if some of you have like the habit of reading things before class and coming, if you think if you learn better that way, then again we will be doing that. We will be like posting, we will be posting the readings immediately after every lecture for the next week. Okay, you may feel free to like read them and come, and there will be like a certain like in class activities like some like the things that you guys did today just now. It's like some warm-up problems basically, and as of now we have not decided if we are going to like have them as extra credits or something like that, but we would let you know like maybe in the next week. Okay, and there are projects and exams. Okay, and projects, there are going to be like 5 projects in the course and 2 parts to each project. So basically you may think of them to be like 10 projects total, and there are like the first part of each project will be in the Linux part, like will be on the Linux operating system, where you will be writing mostly C code, and the second part of each project is going to be in an operating system called XV6. Okay, it's like a very simple operating system that was designed basically for teaching OS, and we will be doing most of our projects there. So for example, one of the interesting coolest projects that you will be doing is you will be writing your own scheduler. Currently XV6 has like a very simple scheduler. We'll talk about what schedulers are, and you will be writing your own scheduler. And these things will be graded on the CS department lab missions. So I hope you guys have access to those Linux missions. You can SSH to those missions. Am I right? Okay, so just make sure that even if you work on your... So how many of you don't have access to those missions? Just raise your hands.
Is it the same ones that we were doing previous class on?
Yeah, so it will be more like royal.cs.risk.edu.
I mean, but like we can access them electronically.
Exactly, you can access them like using the SSH. Yeah, so those are the missions where the TAs will be grading your projects on. So even for some reason, if you are working on your local missions, it is your responsibility to make sure that your projects compile and run, and it passes the test cases on the departmental missions, because while grading, the TAs are not going to do anything, they're just going to run the tests, that's it. Okay, so basically you can pre-grade your projects even before you submit them. Is that a question? And yeah.
What about like comments and formatting and such?
So comments and formatting.
Like we have to be exactly.
Yeah, so here we have like a program called a linter. Most of you would be like familiar with that, like a lint program or linter, which has some specific rules in it, and it checks for those rules in your code base. So all you need to do is like write your code, run that lint program. It shows you the deviations from the coding guideline or something like that, and then you may just go and correct them. And comments, again, we really don't grade you for comments, but as you know, like it is in your own interests to write comments, especially for the XV6 part, where you are not going to write a program from scratch. You are going to modify the code from in a pre-existing code base, which is actually which is not like a huge code base, but it is like a complex code base, basically. Okay, so it is in your own interest to write comments, so that I had like students in the summer who would like forget what they just did like 2 days back, and when they are coming to office hours, they will be like totally confused why they wrote the 3 lines of code there. Okay, and so it's better to definitely write comments in your code. And again, you will not be graded on comments, but you will be graded on the style based on the lint program. Okay. And exams. Again, I think I'll just go to the course web page. So most of the things are here in the course web page. We'll go to the topics in a moment, but exams, the link to exams is here. So there are like 2 exams in this course. It's a midterm and a final, and the dates are given here. Both happen on a Friday, like 7:25 to 9:25. And as I mentioned in the email that I sent you guys, like if you have any conflicts on these 2 days, let me know before the end of next Wednesday. Okay. And the rooms haven't been decided yet. Yeah, this is the grading scheme. You have 5 projects, each worth 10% of your grade, and there are 2 exams, each worth 20% of your grade, and there are going to be like worksheets. So worksheets are like take-home assignments kind of, where you can refer the textbook, or you can use the internet, or you can do anything, but just make sure that you do it on your own, because most of the questions on the exams are going to be similar to the worksheets or based on that, something like that, okay? So if you're confident with the questions on the worksheets, then you can be pretty sure that you will do well on the exams. And there will be like 1 worksheet every week. So we have 15 weeks in total, so we'll be having like nearly 15 worksheets. Any questions till now? And for the course communication, the primary thing is the course web page. All the details will be updated there, and both the TA and me will be using the class mailing list and Piazza for communication. And just make sure that you are logged into a computer right now. Just make sure you go, and the link to Piazza is here. If you just click that, you will be able to sign up for Piazza. Before we proceed to the question, I will again, at a very high level, okay, the course is split into 3 parts. We are going to discuss about the orange part stands for virtualization. Okay, we are going to discuss about something called virtualization. We will go into much more details in today's class. And then we are going to discuss this gray part here. We are going to discuss about concurrency or multi-threaded programs, or like how multi-threaded programs work. And in the last part of the course, the green part here, we are going to discuss about persistence or about file systems. Okay, so let's go into much more details in a moment. And here we have the basic information, and we have the office hours schedule here. Okay, so this is the office hours schedule as of now. And then we have the link to Piazza, and again about the books. The required textbook is OSTEP, Operating Systems 3 Easy Pieces, and there is another book available online which is for the XV6 projects. I would highly recommend you to like go through this textbook to understand XV6 in a better way, but it is not required. If you can just understand XV6 by navigating through the code, well and good, you can just do that. But if you need like some additional help to understand XV6 code, then this is a great resource to learn XV6. Okay, it's again freely available online. And here, this is again not like a required textbook, but it is if you need to learn something. For example, you'll be using a lot about function pointers in C. Okay, like function pointers will be used a lot in XV6. If you want to like refresh your knowledge about function pointers, just go and read the particular chapters in K and RC. Okay. About the books. Projects, the first project will be posted sometime, I think tomorrow, okay? First project will be posted tomorrow, and it will be like due in a week or so, approximately a week. And it is the easiest project in the whole course. So many students in the previous semester when I taught this course, they were, misguided by the level of difficulty of this project and the second project, because this project is will be really easy, you can get it done pretty soon, but project 2 will really show you what operating systems is all about. Okay, so again, this is just warning that don't just think that the level of difficulty of project 1 will be the same as the level of difficulty of the other 4 projects is going to be something similar to project 1. It's not going to be so, because project 1 is too easy. Okay, and project 1 is an individual project, and most of the projects are going to be individual, but for some harder projects we may ask you to work optionally in pairs. Okay, and again, worksheet, the first worksheet is also will be released sometime tomorrow, and it will be due in a week. And worksheets, just make sure that it will be collected in class. Okay, so you need not attend lecture in the sense if you have something, but you can just, at least you should just give it to your friends, or just make sure that your worksheet reaches here. We wouldn't be collecting worksheets online, you can't just email us the worksheets. Okay, yeah, I think almost we discussed everything. And okay, yeah, this is so now this is the grade cutoffs for the letter grades that we have. If you score more than 90 in this course, you can be pretty sure that you are going to get an A grade. And if you score more than 85, then you can be pretty sure that you will get at least an A, because we at the end we may curve up, but it will be we will not actually curve down in the sense. So if you are getting 86, let's say, as your final points grade, you can be very sure that at least you are going to get an AB in this course. Okay. Yeah. Any questions about the course logistics? Anything that we just discussed? Okay, and I think, as I told, I'm looking at these as 3 separate parts. So we'll be taking 2 breaks in between, 10-minute breaks. I'm not very sure, how much breaks did you have when Ramsey taught 354 here?
About that, like that.
2? Okay. So I think now it will be a logical point to take a break, because once we come back, we are going to start discussing about operating systems. Okay, let's get started. So yeah, before I even say anything, I would like to get your views on what do you think is an operating system. So
Mother program.
just raise your hands. Yeah.
The main program that controls all the other programs?
Awesome. So the first answer is it's the main program that controls all the other programs on a computer. Great. Yeah.
Program that controls a computer's resources and hardware.
Wonderful. So the answer was a program that controls a computer's resources and hardware. And by resources, what do you mean?
How much memory, RAM, hard drive, etc.
Awesome. How much memory, the RAM, the random access memory, the hardware, the disk that the program uses, just to control all those resources. Wonderful. Yeah. Great. So it's the software, operating system is a software that makes abstractions about the hardware so that other programs don't need to really worry about communicating with the hardware at a very low level, but instead they can communicate with the hardware at a very high level using the abstractions that the operating system provides. Wonderful. Any other answers or any other things that comes to your mind whenever you hear the term operating system? Okay. So the answers that we got are like one of the things that I would like to like manages the resources, so we can assume it to be like a resource manager. Okay. And the first answer I think was like it is software that actually controls all the other programs and the things, so you can think of it like a control program. Control program, and other thing it's like it's used to, let's say, provides, I would say it would provide an interface to the hardware on a computer. Okay, and so that is why whenever we think about operating system, we can think of it like a layer right in the middle. If this is the hardware of a computer, and if this is the application programs that are running on the same computer, then you can think of the operating system to be right in the middle, which knows how to communicate with this hardware, and also it knows how to communicate with these application programs, and in turn helps those application programs to communicate with the hardware. And what are the main pieces of hardware we are talking about here?
Memory and CPU.
Memory. So definitely we're talking about memory. So, or RAM, random access memory, or DRAM. And what are the other hardware devices or the important hardware devices that we are talking about here? CPU, excellent. CPU, and one more, disks. So we have something called the HDD, or the hard disk drive. So we're talking about all these three hardware devices. So throughout this course, we are going to talk about these three devices, or like how the operating system helps the application programs to communicate with these three devices. And just actually got these three devices here. So this is the RAM, okay, and we have like a sample processor here, like a very old processor, and then we also have the actual hard disk here. Okay, so these are the three things we are going to see. Like, okay, if these are the resources on a computer, important resource on a computer, how is the operating system going to help manage these resources? Basically, is one of the views that we can think about an operating system. And so one important thing here is, okay, that is just like, we can assume that in this computer there is just a single CPU, okay? There is just a single CPU, one CPU, okay? Just like one CPU. But currently it is not reasonable because most of the computers have like multi-cores in them. But if we assume, for simplicity, if you assume there is just a single CPU, then how does multiple programs share the same CPU? It means like we know like we would be able to like run multiple programs at the same time. We can open a terminal, we can open like a word processor, we can open like a Google Chrome web browser, and all these three, let's say in this example, these three programs are going to use the same single CPU on this particular computer. And from the perspective of the user, it is as if like all these three programs are running simultaneously or at the same time. But internally, it is the operating system which actually takes this resource, which is the CPU, and it helps to time share that particular resource among these three applications, the word processor, the terminal, and the and the browser, basically. Okay? And in a similar way, when multiple programs and multiple application programs are running on a computer, we just have like a single memory. So from the program's point of view, main memory is nothing but an array of bytes. So if you have like, let's say for simplicity, let's assume there are just 16 bytes in this computer, so 0 to 15. So if there are just 16 bytes on this as the main memory, it is like unrealistically small, okay, but it serves this purpose right now. There are just 16 bytes that we can use as the main memory, and if there are like 3 applications that are running in this computer, then how is it possible for these 3 applications to use the same main memory without overwriting, okay, without overwriting some parts of the memory that other applications are using? Does it make sense? So here, to answer this question, again, we need the help of the operating system to make sure that no two applications, overwrite the memory, like no applications overwrites the memory locations that some other application is using. Okay, the operating system helps us in this case. Basically, what we just did now is like we just virtualized. We are giving an illusion to the applications that it has its own CPU. To each and every application, the operating system gives an illusion that it has its own CPU. And it gives an illusion to each and every application that it has its own memory. So the first way to look at an operating system is it is actually used to virtualize the resources. Virtualize the resources. Okay. And in other words, so operating system is also called as a virtual machine. Okay, it's called a virtual machine. And this another way to look at an operating system is more like a standard library. So basically, if you think about an operating system, okay, so how many of you have like used C++ in any development that you have done here? C++ programming language or anywhere? Okay, great. So like in any programming language like C++ or Java, okay, we have something called a standard library. Okay, a standard library provides a lot of like features which the programmers can use so that they need not like rewrite functions like, let's say, sorting, okay, or searching. You can just use binary search. You can just use those features from these standard libraries. Something like sort, something like a binary search. Okay, and in a similar way, okay, the second view, the way we can view an operating system is as if it is a standard library. We think of an operating system as a standard library that provides some functionalities to the applications that are running on top of it. And for example, okay, the things are, if you want to communicate, if an application wants to communicate with the hard disk, okay, if it wants to like read or write some data into the hard disk, we have features, or like we have APIs like read, we have APIs like write, okay? And in a similar way, if an application wants to do something related to process creation, don't worry about what process creation means right now, but we have some APIs called fork, which creates a new process. And then if an application wants to increase its heap, again, since we assume that you guys have like took 354 before, okay, it would be like we would really assume that you have really learned it in a good way. So here when I just told, okay, how can an application, what is the system call that an application uses if it wants to increase the size of its heap? Malloc, one of the answers is malloc.
mmap,
Any other answers? mmap? Any other answers? Okay, so one more question is like, is malloc a system call? Let's talk about system calls maybe much more detail later, but actually malloc is like a C library function, which in turn, okay, malloc allocates memory on the heap, but which in turn calls a system call called sbrk, sbreak. Okay, this is the actual functionality that the operating system provides for increasing the size of the heap for a specific application program. Okay, and application programs can also call this function directly. Okay, and the functions that, and these APIs, these are just like the APIs, right? These are just like the APIs, application programming interface, and these APIs that the operating system provides have like a special name. Okay, the APIs that the operating system provides have like a special name, and these are called system calls. Okay, system calls are the APIs that the operating system provides to the applications. Okay, using these APIs, the applications can do privileged operations. For example, writing to a disk, okay, let's assume writing to a disk. If applications can write to disk on their own, what may happen? If applications are given the power or like the privilege to write to disk by themselves, okay, then what may happen? Pardon? Exactly, we can just overwrite protected information, and we can overwrite the files that other users have created on the same system. Many things can happen, right? And that is the reason why the operating system provides a way in which, or the only way in which applications can write to the disk. If any application wants to write to the disk in a file, it has to use this system call called write. And when the system call is used, the operating system is invoked, and the operating system makes sure that the place where we are going to write, let's say, application A's content is not some file that is already existing on the disk. Okay, and so any questions about this? Why we treat the second view? Okay, these are the how do we view the operating system? Second thing is like a standard library to applications. Any questions about this? Yeah. And again, the third view, as we saw here, okay, from that we got from the students' answers, is just like OS is nothing but you can view the OS as a resource manager. These are the three ways in which you can view the operating system. Resource manager. It's like a virtual machine, it's like a standard library to applications, and it is a resource manager. Okay, so in our course, as we just discussed this, the way our course is organized is in this way. Okay, the first part of our course, we are only going to discuss about virtualization, or we are going to view the operating system as a virtual machine and see how it helps us to virtualize two main resources. The two main resources that we are going to focus are the CPU. The first thing that we are going to discuss is how the operating system virtualizes the CPU, And the second thing that we are going to see is how the operating system virtualizes the main memory or the RAM. Okay? And the second part of the course, okay, in the second part of the course, these are the two different shades of orange that we saw here. Yeah, so the first 2 weeks, week 1 and 2, just discuss about virtualizing the CPU. Then weeks 3, 4 and 5, we are going to discuss a lot about virtualizing the memory. And then in this week 6 to 9, we are going to discuss about a topic called concurrency. Concurrency, or think of them as threads. So how many of you here have written or have any experience working with multi-threaded programs? Okay, great, at least 20 of you. So here we are going to go into a lot more detail about how concurrency works. But if you think about it, till now, the way that we viewed the operating system, we did not talk anything about concurrency. So concurrency, we'll give you an intro in today's class, but concurrency is basically, we will be writing programs, okay, which will have sub-programs within it. So for example, if you're going to write a web server, there are going to be some sub-tasks within it. First, and we are going to call them as threads, okay? And each task will be responsible for doing a particular thing. So each thread will be responsible for doing a particular task. So in that case, it's going to be more like if you're going to write a web server, if this is a web server, okay, there may be multiple threads running here, and let's say thread 1, okay, thread 1's job or task will only be to just accept incoming connections. There may be multiple clients trying to connect to this web server. Let's assume this is like a Google server, okay. Multiple people will be trying to connect to this particular server whenever they type www.google.com, and there will be one thread within this particular program, web server program that will be running, that's whose sole responsibility will just be to accept connections. Accept connections, okay. And there may be another thread, let's say thread 2, where it will be once a client got connected, thread 2 will be the thread which will be doing some processing for that particular client. So this is do processing. Or let's say one client, okay. So in a similar way, then we may be, for each and every incoming connection that is being accepted, we will be having one thread that is created for handling that particular client. So there can be there may be n number of threads based on the number of clients that we will be having. This is at a very high level. So it is just within a single program, we will be having multiple sub-programs kind of, which will be taking care of some specific tasks. Okay, we will look at some examples in this class. And the third part of the course, the green color part in the course web page, just discusses about persistence. All it says is we have this device called hard disk. Okay, how does the operating system manage this particular device, or how does data stored on this particular device? Okay, we will go into much more at a very much more detail into that. Okay, so this is how the course is organized. Again, you see these are the 3 parts. Okay, and okay, so let's now go and see some examples. I'm just switching to my lab computer. Is this font visible to everyone? The back, shall we increase it? Okay, we have some files that we're going to look at in this class. The first thing is just cpu.c. Okay, this is the first thing that we're going to discuss. Let's take some time to go through these lines of code. Try to understand what this code snippet is doing. Does anyone have like a laser pointer by any chance? I think I forgot mine. I don't know. Can I use it?
What do you think of the cat pointer? Like a mouse.
Okay, so this is like pretty straightforward. What we are seeing here is we here we are just checking if the program takes exactly 2 arguments, and the arguments are, the first argument is just the name of the program itself, and the second argument is just some string that is given there. And if it is not the case, we are asking the operating system to exit this particular program, terminate this particular program. And then in this line, we are just like taking that argument that we got from this argv and assign it to this particular string. And then here we just go in an infinite while loop, and we just keep on printing that particular argument that we just got. Okay, just doing that. And the spin here, okay, this spin here is just like, you can think of it as just like a sleep. Okay, it's just like sleep for 1 second. It is like defined. So currently I have these files, right? I'm going to just do something called tags, okay, to navigate between these things. And in Linux it's like C tags. And if you give this C tags -r star, it creates like an index of all the functions that you have. And after that, if I just open this and if I want to see what this spin is, I just go and do a control and a close square bracket, and I just go to that spin function, which is there in a file called common.h. Okay, the file's name is common.h, okay, and which we have written, which is there, and it has this spin function. If you want to know, you can go into the details of like how this works, like just like a delay. So this is Vim. The thing that I'm using is Vim, and it has some plugins and stuff like that, and that's what makes it so fancy. Okay. And yeah, so it just waits for a second before it prints the same string next time. That's all it does. And at the end, why do we have this return 0? Anyone? In the simple program, yeah?
To show that it returned normally, or that it quit normally?
Exactly. So the return 0 is the way that the application programs informs the operating system that it has terminated normally. And this exit 1, okay, this exit of 1 will actually in turn like return like something like 1, something like that, some different value other than 0. Or if here you could have just wrote like return -1 or return 1, where the operating system would have understood, okay, this program did not exit normally it just exited due to some error conditions. Okay, and that's why we have this here. And now we are just going to compile this GCC -o for the output file's name. I'm going to just name it as CPU, and this is the file that I'm going to compile. And I'm writing -w all, like treat all warnings as errors. And it says like something like in function pthread create undefined reference to pthread create. So in this file called common.h, okay, we have some things called pthread create, pthread join, stuff like that, which you need not worry right now. But we need to add like a command option called pthread, like a linker option called pthread. We'll go into details about this when we go into the concurrency part, okay? When you give an introduction to concurrency, but if you just add this, it will compile normally. And then now if I want to execute this, all I just need to do is /CPU and give a string here, right? Like something like epic. Okay. All it does is just prints that continuously. And how can we terminate this program?
Interrupt,
I interrupt, like how do I interrupt?
control E, I think it is.
Control?
Like
Control C, yeah. Control C sends a kill signal to the particular program from the terminal, and so if I press like Control C, we just stop this, okay? There's nothing like fancy happening here, it's pretty straightforward. But now the interesting stuff happens when
Is
we,
that considered like a return, like from the program's point of view? Like, is it gonna return 0, or is it just do nothing? When you control C.
no, it's just going to like stop wherever it was executing. So the question was, when we just did Control C, will it go through the process of normal program termination by returning 0? Okay, and answer is no, it is not going to go through that process because it is executing within that loop and it just terminates right there, wherever it was executing. Okay? And what does this mean? If I add an ampersand at the end of this, what does this mean? So it just means that we are going to execute the same program in the background. What do we mean in the background is, okay, let's execute this, okay, I'm just executing this right now. You get the process ID. Whenever you run a program, it is given a unique ID, and that is the unique ID for this particular program that is executing, and now it is executing. But if we try to do Control C right now, okay, I just did Control C, okay, just do Control C like continuously, but still I'm not able to stop this particular program from the terminal because currently this program is not connected to this terminal. It is executing on this computer, okay, it is executing on this computer, but there is no way that I can communicate with this particular program from this particular terminal because it is executing in the background. It is just using this terminal to print its output, but it is actually not connected to this particular terminal. Does this make sense? And so, how can we terminate this program right now? Pardon?
Kill the process.
Kill the process? Yeah, we can kill the process. How can we kill the process? So one way to terminate this is we can open a different terminal, okay? You can open a different terminal and find out this process's PID. Okay, again, I need to first log into my computer. So if I just do PS, lists all the processes, PS, AUX, these are some options that are given to the PS command. PS stands for the process command. And I'm going to grep for this thing called CPU. It's the name of the program, right? So if you see here, it shows that this program is running with the argument called epic, and it has a process ID of 29096. So what I can do is I can just do kill is a command that is used to send a signal to a particular program, and if I do kill -9, then it sends a SIGTERM signal. SIGTERM means signal to terminate that particular process, okay? it sends this particular signal, and if I just give this particular process ID here, okay, so whenever a program starts executing, it is no longer a program, it becomes a process. Okay, we will be discussing about that in more detail in today's class, but it just becomes a process. And so in this case, I'm going to kill this particular thing. So did you just notice it here? When I just did that, here in the other terminal, we just got killed, and this was killed. This particular program was killed. Now if you go back to that terminal, you can see that we will be able to write some of the commands in that particular terminal. So I just did this. Any questions? Yeah.
What is the 1+?
I have no idea. So I have no idea like what this 1+ is. You can go into the details and you can check it. But pardon? Does anyone know? Sorry, sir, I'm not able to hear you. Sorry.
It's the job number that was assigned to it from the batch quite often in the background.
Got you. Okay. Okay, great. I think it would be, from whatever I understood, then it would be helpful when multiple jobs are running in the background, and if you want to skill like a specific job, right? Okay. Great. So I really don't know about that, but yeah, as you just told, like, let's try that. So you're saying you run this and then run jobs. The other terminal, right? Oh, okay. Let me connect it. Okay, this one? Okay, I don't understand it. I'm not able to like understand it completely, but we can figure it out, okay? So I'm just searching for this PID. Now the PID, the process ID is different, so I want to kill this. So I kill this. Okay. And one more way that we could have done this is using, when it is executing like this in the background, we could have typed a command here in the same terminal called FG, okay? FG just stands for foreground. Once this is typed, now in that same terminal, that process is brought to the foreground, okay? And so now if you press Ctrl C, you can actually terminate that particular process. Okay, this is one other way to kill a background job, and why we are discussing about these things is now you can actually run the same program twice with two different options. So what I'm doing here is I'm running the same program first with the argument called epic in the background, and on the same terminal, as a part of the same command, I'm running the same program one more time with the argument called UW-Madison, and it also runs in the background. And now, for simplicity, let's assume that this computer, okay, that I'm using has like a single CPU, okay, because this is going to work even if there was just a single CPU, but definitely my computer has like a many number of CPUs. But even if my computer has like a single CPU, if I run this particular thing, what is going to happen? Any guesses? So here we are going to start two processes. This is going to be a process, and this is going to be another process, and two processes are going to execute on the same computer which has the single CPU, and the operating system in between just makes sure that it virtualizes the CPU. Okay, it gives an illusion to these two processes as if it has its own CPU, so that both are going to just execute continuously. In a sense, if I just do this, you can see here that the first process prints epic continuously, the second process prints UW-Madison continuously, but they are doing it in like in alternate fashion. Yeah.
If you do FG now, will it bring them both? Which one will it bring to the foreground?
Yeah, one of them would be brought.
One of them?
Yeah, just one of them. So if we do a FG now on this terminal, one of them would be brought to the foreground, and then you can just terminate that, and you can do another FG and kill the other one. So you can just do something like FG. So now UW with the UW Madison has been brought to the foreground. You can kill that. Still the other thing will be running now. You can see here that just the epic will be running right now because it is still running. Now bring that to the foreground again and then kill it.
Could you connect a different terminal window to one of the processes once it's in the background running? So let's say you want to see that output in the foreground in a different terminal window.
Yeah, I'm actually not sure about it. So does anyone know it? Like, can we connect? For example, we make a process to go to the background in a terminal window. We can just try that and try bringing that process to the foreground in a different terminal window, right? I think it should be possible. Okay, the question is what happens when we just do this, but open a different terminal window and try to bring this process to the foreground, right? I don't think so. Nope.
The process ID, just not connect to it. We don't know the process ID.
Yeah, so there may be some ways definitely that we could do. We can just like search how to do that. Yeah. Any other questions? Can we do that? Is it just FG with the job ID? Yeah, we can actually, definitely there may be some way, but you can figure out the details. Okay? And now I'm just going to bring this to the foreground. Okay, and this is like a simple, very simple demonstration of how like the CPU is virtualized between multiple processes. Okay, and then now the next thing that we're going to see is something about memory virtualization. Again, it takes some time to go through this particular piece of code. Important thing starts at line number 7. Just take a minute to look at this and then we'll discuss about this code. Try to understand what this is actually doing. You can remove some unnecessary details there. Just focus on this as of now, and then we can do something. Okay, I think let's discuss. So again, we're not going to discuss about the error handling here. We have a pointer, okay? P is just a pointer. And I think it would be better if we could draw some diagrams along. So let's divide this. Okay, we have like the P. It's just a pointer variable, okay? Just create it here, the pointer variable created here, and then we assign it to we have this value to be a global variable that is defined here, okay? And here what we just do is, just store the address of value. So value we can think is just this variable, value, okay? And let's assume as of now it is at address 100 in hexadecimal, so 1000, and we are just assigning in line number 15, we are just assigning the address of value inside P. So all that happens here is this value just goes here. After that, what this means is P is pointing to this variable called value. That's all that's happening here. And then we are asserting if P is not null. That is not actually needed in this case. But if you do an malloc, that may be needed. Okay, let's go into those details later. But yeah, again, at line 18, what we are doing is we are just printing the PID. PID again just stands for the process identifier. Each and every process that we run on a computer has its own unique PID. Okay? We print the PID for this particular process, and then we print the address of that variable, address of P. And then we also print something called address stored in P. Okay? So address of P is just like ampersand P. Okay, so here in this case, by address of P, what we mean? So what is the value? Is it shown here? So address of P is actually some value that this P is actually at. Let's assume if this is at 0x200, address of P in this case is just 2000. Okay, and the value of P is just 100. That's what we are trying to print here. And then what does this mean? Like A to I? Anyone? What does this line of code do?
String to integer?
Exactly, it just like takes this string, which is argv of 1 that we pass into this program, and converts it to an integer, okay? Converts it to an integer, and we assign that integer to star P. So in this case, what is the variable that is going to be assigned this, that is going to get this value? Pardon? Value, that's it. So star P here, or asterisk P, just means that you have P, the value that you're going to store is not inside P, but wherever P is pointing to. So the value, let's assume we give an input value of 10 to that program by typing something like ./mem10. That value of 10 is now going to be stored inside this. That's all is happening in that line of code. And then we again do like infinite loop, and we just go and increment that value inside star P, which is the value inside the global variable, by 1 each time. Just print that value, spin for a second or like sleep for a second, and then just do that continuously. That's all this program is doing. Any questions about this? So now what we can do is try compiling this. Okay. So ./mem, if I just do this, it will throw an error saying like this is the usage. If I give 10, it's just going to print 10, 11, 12 continuously, and I can terminate it, okay? So now you can see here, the address of this variable P is this value, and the address stored inside P is this another address value which is small, okay? Now, questions here, okay? So now what we are going to do is, we are going to try running this in the background and try running another version of the same program, let's say starting at 1000, okay, in the background. And let's see what's happening here. So if we just see here, the address of P is actually different, like in the sense, the address of P in this first process with the PID of 29641 is something 7FFF, some value, but the address of P in the second run of this program is a different value, okay? But usually, okay, this is being done even though both the processes are actually using the same, like a variable called P, okay? Here we have like some different values, don't worry about this, but right now I am going to like give an option, okay? You may make a note of this if you want, but I'll explain like what I am doing here in a moment. So by giving this option, I just told the Linux operating system not to like randomize the address spaces. By that I mean, whenever I'm going to run like two versions of the same program, okay, both, if there are two variables, corresponding variables, in this case let's say the variable P, okay, in both the versions of that program, it is going to be assigned the same address, okay. Now let's see that, okay. So if I run this thing like /mem 10 /mem like 1000, so now can you just see here? Okay, so the idea here is this, okay, we are having like the first version, okay, the first version is with the PID 29676 and the second thing is with the PID 29677, and you can see like both these two processes are exactly using the same address. You see that both the processes are using the exact same address for the variable P. So if we do this diagrammatically, let's just think of what is happening here. There are two versions of this program. Let's just name them to be like mem 10 and the mem 1000, okay. Both these two versions of the same program, okay, are using something called, let's say, a location. This is the variable P, pointer variable P at location, let's say, in this case it was 7FFF E148, okay, at this address. But even though it is using the same memory location, both are able to update its value from, let's say, it is going on updating its value from 10, keeps on going, and this is updating its value from 1000 one by one, and it keeps on going.
Aren't the addresses themselves like, really represent like the real address?
Exactly, yeah.
Yes.
That's the point that we're getting here. So great. So how is this even possible? Okay, if the location, if the memory location that we are talking about, if it is just a single memory location, okay, that is being shared between these two processes that are running, then how is it even possible to do two things simultaneously? It's difficult, right? In the sense, we will lose the previous value, right? So if we have just this single memory location, and if this process has the value of 10 inside it, and suddenly while it is trying to increment it, let's assume if it increments it to 11, And before it does the next thing, if this process is also using the same memory location, and in turn, if it uses this thing, if it writes like 1000 here, then the 11 is gone. There is no way that we can restore this value of 11 back for the first process that is running here, right? So how this is happening internally, already one of the students here just gave the answer, but does anyone want to give a try?
Using two different physical addresses, and it's just virtualized. So you're taking something here, giving it a different virtualized address. You're taking something else, giving the same virtualized address, but two different tables referencing different physicals.
Exactly, amazing. So whatever address that we see, okay, or the program sees are just virtual addresses. So in this case, okay, these two programs in this case are thinking, okay, these two programs, let's just again name them like mem10 and mem1000. These two programs are thinking they are accessing a memory location like 0xFF something E148. It is also accessing the same memory location 0xFF E148, but actually these are not the physical memory locations on the computer, on the main memory. In the main memory, if this is the main memory, this is the memory of the computer, the OS does something to make sure that this process's memory location FFE148 actually refers to some location here, which can be something totally different, like 1, 2, 3, 4. And other processes, E148, actually refers to some other location, which can be totally different, like FF1279, something like this. Does it make sense? So the OS helps us to actually virtualize memory. Even though two processes are thinking that they are accessing the same memory location, internally, behind the scenes, the OS virtualizes the memory in a way to make sure that each process has its own memory in the actual physical memory or in the RAM. Okay, and this process is called memory virtualization, and this is like a very high level. By the end of the 5th week, you really understand, like the devil is in the details, right? You really understand how this works when we go into much more detail about how memory is actually virtualized. Okay? Any questions about memory virtualization? Yeah. Pardon? Yeah. Exactly, yeah. That's a very good question. So, why did the same variable p, okay, when we ran it in two different versions of, like two different programs, were assigned different addresses is due to security reasons. If Linux always uses the same address for the first variable, and if it always uses the same address for the second variable that used in a program, then it was like that before, okay? A few years back, it was actually like that. The address spaces were not randomized, and people actually started, understanding much more details about how these programs work, and there were like a lot of attacks that were happening. You can easily, there are some attacks like buffer overflow attacks, which you can, if the address space is not randomized, you can, like once the program is loaded into memory, we can easily go and access other programs' data and stuff. Okay, and so that is the reason why by default currently Linux randomizes the address space, and if you give that option, we are explicitly asking Linux not to randomize address space for that particular run of this like terminal kind of. Okay, good questions. Any other question about memory virtualization? Okay, great. So I think like, okay, at this time, now we can discuss the next thing, which is the concurrency. Again, take like a minute or two to just go through this. Again, we will be discussing it.
Can you flip it?
Oh, sorry. initial 3 lines are just include lines, and then you have the program start at line number 5. Maybe I think we will just start discussing this because I'm not sure, I think most of you may not be aware about threads, okay? So here, what we're doing, we'll start from main. Again, we're just checking for the error conditions, and then here we just take the first argument, do ASCII to integer. A2I just stands for ASCII to integer conversion. Just do the conversion, convert it to integer, and assign it to the variable called loops. And then in this line number 22, we actually create 2 threads within that process, okay? It's a single program, okay? And when it is going to run, it becomes a process. Now, while it is running, this line says that, okay, I'm going to create 2 processes. It's not like it is not being created here. Here we are just declaring 2 variables of type pthread. Again, pthread stands for POSIX threads, okay? They are the type of threads that we use in C, C++. And here in this line number 24, this is the line which actually creates the thread. Okay, here we say we are going to create a thread with which is like a P1. We are giving the address of this P1, which is of type pthread, and this underscore T just stands for type. It just means this variable is of type pthread. And then don't worry about these options, okay? Don't worry about arguments 2 and argument 4 as of now, for simplicity. The argument 3 here just says, once this thread is created, immediately start executing this function called worker. Okay, that's all it does. And then, again, in the line 25, create the next thread, P2, thread 2, and again, when this thread is created, go and execute the same function. But basically, we could have actually executed a different function called worker2 or something else for the second thread. It is possible. But in this case, we are just executing the same function called worker for both these threads, okay? Threads P1 and P2. And then here 26 and 27, 26 just means now the main program is running, okay? Okay, one important difference between what happens when a pthread create happens is it is not like a function call. Okay, what do I mean by it's not like a function call is we really don't wait till this line completes. Okay, when a thread is created, the first thread goes and starts executing this function, but we don't wait for this function to end, okay, to complete before we proceed to line 25. We don't wait. It is asynchronous. Okay, we start 24 immediately, even though we may be at line 11 or somewhere, we immediately go to 25 and start this. So the second thread is created, and again the same worker gets executed, the worker function gets executed in the second thread. So after line 25 happens, 2 threads are actually executing the same function worker concurrently, okay, concurrently. And this join just says, can we just wait for the first thread to complete before we proceed? So now here it means, okay, at line 26 it means only we will be able to execute line 27 only if thread 1 finishes. Okay, we are waiting for thread 1 to finish. Join just waits for thread 1 to finish, and again the line 27, in line 27 we are waiting for the second thread to finish, P2, and at line 28 we can be sure that both the threads P1 and P2 have completed, and we are printing some final value. Okay, so now let's see what this function worker does. Worker, okay, what it does is we have like a global variable called counter. Okay, we have like a global variable called counter, which is like integer, and the volatile here just informs the compiler, okay, the volatile keyword here just informs the compiler not to perform any optimizations with that particular variable, okay. It just has that variable as it is, it doesn't perform any like optimizations with it. So here we have this counter, and inside this we are just incrementing this counter n number of times. That n just is that loops time, whatever we give that particular program, okay. So let's assume now if we give a value of 10, initial value of 10 to this particular program, what is going to be the final value? Just remember, two threads are incrementing. The first thread will start this worker function. It is going to increment this counter 10 times. The second thread is also going to do the same thing. It is going to increment the counter 10 more times. And what is going to be the final value? And again, counter is a shared variable, okay, between these two threads. They are not like different variables. Counter is a shared variable between these two threads. Threads share memory. So what may be the final value?
20.
Pardon?
20.
20, yeah. Awesome. So simple. So it's just going to be 20. So here if I do like compile this, gcc-o threads version 0, then sorry. So whenever you are using a multi-threaded program in like C, you have to give this linker option called -pthread, and only the linker will understand that we are using like a threading library. Okay. So here I just compile this, and now if I run the threads version 0 with the value 10, the initial value is 0, the final value is 20. Okay. So simple. If we make it like to 100, it's going to be, the final value is going to be 200. Right? And you can just proceed like 1000, it becomes 2000. You just go to 10,000, what happened? Something interesting happened, right? Yeah.
So, is increment an atomic operation?
Yeah, that's a great thing. So, can you just wait? You could think, yeah. Great.
Sorry.
So yeah, so we have the final value here. But for 10,000, we obviously expect 20,000, but it came to be some different value. We can run the same thing one more time, and it's much more worse. So if a program behaves like in a wrong way, okay, it is better if it consistently produces the same wrong result, right? As software developers, most of you know, like if the second time when it runs, now you can see like it produces 15372, which is the worst thing that can happen to the program, right? It is wrong and it produces like different wrong results at every run of the program. See here, it's 17691. Why is this happening? You guys think? Pardon? So one of the things is it overflowing an integer? No, because it's like very small value. We are not worried about overflows here. Any other ideas? Pardon? Exactly. So both the people here and there, they got the answer. So the reason is, okay, the reason that this is happening is, if you remember the first like student introduction worksheet that I gave you, okay, I asked you to like mark the region in the assembly code, okay, that corresponded to the statement counter plus, right? So let's see that same thing again here, okay? What we'll do is I'm just going to compile this. For simplicity, I'm going to compile this with for a 32-bit machine, okay? This is going to compile this for a 32-bit machine, which just means the address values of the addresses are going to be like smaller, okay? Just going to do this. Now, if you run the same thing, okay, now it is like, okay, I have some problem here. This is specific to my computer, don't worry. Okay, I have like multiple setups. I'm not going to do that. Let's just have it for, I can do that and then I can just see. I'm using like object dump now. it's a program called object dump, and if you do like a disassemble option, and you can give this threads version 0. So you see the assembly code, and I'm going to the assembly code for the worker function, which is here, okay? And here we can see the actual answer for the thing is like the counter plus plus. Again, maybe we can see the actual C code once before we come here. So the C code is here, right? The counter plus plus, the single line here gets transformed into multiple lines here. Single line of C code gets split up into like multiple lines of assembly code. This is the answer for that particular question, okay? The counter plus plus, what is happening here is we have this line, the first line here, we are moving the value from this memory location to a register EAX, and that memory location corresponds to the memory location of counter. Then we are adding 1 to the register EAX, to the value that is inside the register EAX, and then we are again moving the value inside the register EAX to the same memory location, which is counter. So let's assume if this is that memory location 0x8040 something, okay, and if this is the EAX register, all we were doing was, if this was initial value was 0, the first move instruction just copied this to the register, okay. Then the second add instruction just added 1 here. Then the third instruction move again moved this value here. So now we have incremented this counter. This is the value. This is the variable counter. Okay, we just incremented the counter by 1. Okay, by doing those 3 assembly instructions. But the interesting thing is, when these 3 assembly instructions happen, okay, we were executing 2 threads simultaneously, right? We are executing 2 threads simultaneously. There is like no guarantee, okay, that all these 3 instructions are going to be executed atomically. Okay, by that we mean, what we mean here is, let's go into like much more detail now. The 2 threads here, let's assume this is T1 and T2, there are 2 threads. So the important thing is these 2 threads have their own version of EAX register. So by that here we mean the EAX register on the computer is just a single EAX register, but these 2 threads will have like a copy of whatever value that it had in its EAX register, okay? And so let's assume both start at 0, right? So not this EAX doesn't start at 0, so I'm sorry, okay, don't worry about this. Since we just told like the 2 threads are going to share the same memory region, okay? This memory region that we have here, 0x, let's assume 8040, this memory region which corresponds to the variable counter is being shared between these 2 threads T1 and T2. So initially it started at 0, okay? So now let's assume the first move or first thread 1 executes, okay? The 3 instructions are just like thread 1, thread 2, okay? This is the sequence of operations that we are going to consider right now. Move, I'm not writing, let's assume this, move this to EAX, right? If thread 1 executes this instruction, then what happens is, thread 1 moves this value inside the EAX register. Now EAX gets 0. Then now we add, okay, immediately thread 2 adds 1. Thread 2 adds 1 with the value of EAX, okay? Now EAX becomes plus 1. At this time, okay, at this time, if the operating system decides to run the other thread, okay, because these 2 threads are running concurrently, at this time if the operating system decides to run the other thread, then what happens is this thread is paused currently after this instruction, and the next move happens here. Move 0x80, to EAX happens here. Okay, so basically even before this updated value is stored in the counter, now the second thread takes the same value and has a value of 0 in its own EAX. Makes sense? And then let's assume this is not interrupted, all the 3 instructions happen simultaneously. So add 1 to EAX, so 1 is added to its EAX, and then another move happens from EAX to 0x8040. So now this is being updated to 1. Now we go back, now this is again done. Now we go back here, and if we run this last move from here, move EAX to 0x8040, now again this new value of 1 is updated here, but the previous value is already 1, so we update it with 1. Even though the 2 threads have updated the same variable once by themselves, we expect a value of 2 to be here, but just this sequence that we just saw here made the value to be, the final value to be 1. Makes sense? And this is the reason why we were seeing like just some random values when we increased the number of the input that we gave.
Theoretically happen with 10.
Yes, theoretically it could happen even with 10 and even with 100 and 1000, but why it didn't happen? Exactly, so it didn't happen because that loop for the 10 times just finished even before we switched to the next thread. The entire thing got completed even before we switched to the next thread. And that is the reason why it didn't happen with 0, 10 and 1000, but for 10,000, the time that that thread had with the CPU was over, basically. And so we switched to the next thing. And then there we did, and then we switched back, and there were some problems. And
So
Okay.
is it because you said you put that volatile thing in there to tell it to not optimize? So if it like was able to optimize, would it be bothered?
no, so the volatile there does not really matter. Yeah, it just happens even with the normal integer. But the reason is this. In the sense we really don't have any control over how the operating system schedules different threads, okay, on its CPU, and that's why it happens. I think we can take another break right now, okay? We can take a break of 10 minutes, and then we will. So how can we address this particular problem? Like how can we make sure that that the OS does not switch between threads at some critical points, like after it does an addition, but before it stores the value back to the memory location? Exactly, yeah. So the answer is we are going to have something like a lock, okay? This is the next version of the same thing. So the only change that we have made in this code, the only change that we have made here is just like lines 12 and 14, where we are actually doing something called pthread mutex lock, okay? Don't worry about the details of this. Mutex just stands for mutual exclusion, okay? And we are having like a lock here with m, and m is just like of type pthread mutex, okay? We are doing a lock and then we are doing an unlock of that particular mutex here. So all this means is we are telling the operating system that this line of code, counter plus plus, in turn in assembly, which translates to 3 lines of code, should be executed atomically. Okay? So, or the one more way to look at the same thing is like while thread 1 is within that particular region is called the critical section, okay? The critical section where if two threads run the same piece of code in the critical section, then bad things happen, right? And so when thread 1 is doing this counter plus plus or is executing within the critical section, thread 2 cannot execute the same critical section because it cannot acquire the lock. Thread 1 already has the lock. Yeah.
Since there are multiple processors, what's to stop your computer from having 2 different processors trying to acquire the lock?
So you're talking about multiple processes, right?
Yeah.
Yeah, that's a very good question. So the question here is, okay, what happens if we have like multiple processes? In this case, if we have like 2 processes, then thread 1, if it is executing on processor 1, and thread 2, if it is executing on processor 2, then these things are actually not needed, okay? But
Couldn't they both try to grab the same lock? At the same time?
But internally, the way it works is like there is like one scheduler for each processor.
So something will make sure there's actually an order.
Exactly. That is like a lot of detail inside that question. Maybe so the question was like about like what happens if there are multiple processes, okay? And do we still need these logs? Actually, yes, we still need these logs. And maybe I'll just skip that thing right now, okay? That's not needed currently, but we'll go into a lot more detail in that. But here, you can assume that in this case, that we have like just a single CPU. If you have like a single CPU, then in that case, here you're locking it and then doing the critical section and then unlocking it. So while a thread is executing in the critical section, no other thread can execute in the same critical section. Okay. Then this is how we avoid it, and then if you try running it right now, let's say I'm going to compile the version 1 now. Just compile version 1 and if I just run that, let's say with 10,000, it is 20,000, even more number. You see it? It is like correct every time because we have logs, okay? And the second part of the course, we are going to go in and learn much more detail about logs and more about like how these logs are actually implemented, okay? And this part of the course, second part of the course, I feel would be like very helpful when you are dealing with multi-threaded programming in real world, which is the common case right now. Okay, no one currently writes like a single-threaded program. Most of the programs that are being written in the real world are actually multi-threaded programs. The last example that you're going to see is about persistence or the I/O. Here in this example, what we are doing is we are just like trying to see how do we interact with the disk. We are opening a file under /dem. The name of the file is file, and we are giving some options for this open. Again, open is a system call that the operating system provides to the applications, where the applications can use the system call to actually create and open files, okay, to read and write into them. And the options are, we are opening this file only for write only. We are only going to write to this file. We are not going to read anything from this file. And this create option just means that if that file does not exist already, just create that file. Okay, while opening, just create that file and then open that file. And then truncate is if some contents exist in that file already, truncate that file to size 0, or basically just delete that previous file and then create a new file in the same name. And then this is like the first argument, and these three things with the OR thing in between are the second argument, and this is for like the third thing is regarding the permissions, okay? You can just go and check what this exactly means. We are giving some certain set of permissions for this particular file, okay? Read, write, execute permissions for this particular user who's creating this file. And then we have like an assert, we are checking this file descriptor if it is greater than or equal to 0. And then we are having like a string here, like basically an array of characters, 20 of size 20, and then we are writing the content of hello world with the \n, which is the new line inside this buffer. And then here we are using the next system called write to write into that file. We are giving this file descriptor. Once we give this file descriptor, now it means that, okay, this file descriptor that would have been returned here, what may be the value of fd? Anyone in this program, what may be the value of fd when we run it? So whenever a process is created or whenever a program is running, usually the operating system assigns 3 file descriptors by default. And they are 0 for standard input, which is the keyboard, 1 for standard output, which is the screen, okay, and 2 for standard error. The error messages would be redirected, and by default it just points to this monitor again, okay? And so FD here, when we create a new file, it will take the next lowest available file descriptor, which in this case is going to be 3, because 0, 1 and 2 are by default already assigned, okay? You get the value of 3, and then here when we pass 3, now for this particular process, the value of 3 just corresponds to that particular file. Whenever we just say write to 3, we mean write to the file temp/file. So we write the contents inside this thing called buffer, which is hello world, and the size of that contents is string length of buffer, okay? Something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, something like 12 or 13, okay? And then we have like an assert, we just make sure that write returns the return type, the write returns the number of bytes successfully returned to the file. So we are collecting that return code, and then we are checking if that is equal to the string length of the buffer, okay? And then we say like we wrote these many bytes, and we do an fsync here. Fsync just means that whenever we actually do a write, okay, the operating system does not guarantee that that write has reached the actual disk. Okay, when we just say write, that write may still be in memory. So from the application's perspective, if the application wants to make sure, if the application program or the application programmer wants to, if the programmer wants to make sure that that write is definitely or actually persisted to the disk, then they need to do this, call the system call called fsync on that particular file descriptor. So now when we say fsync for this particular file descriptor, then the operating system actually makes that write to the disk. If we did not have this line 16, okay, if we did not have this line 16, and if a crash happened, let's say after line 15, okay, if the system crashed after line 15, when you come back and when you reboot the computer, you cannot be sure that the file temp/file contains the content hello world, okay? But if you do fsync, and if your system crashed after fsync is complete, then you can be sure that that file will contain that particular thing. But if fsync is not there, what will happen is like at certain, let's say after 30 seconds or something like that, those writes will actually take place on the disk. Okay, we will discuss a lot more details, much more details in the third part of the course, which is about persistence. Then here we just close the file descriptor, and then we are done. In the main, we just call this function called do work. So if we just run this, again, even though these particular things don't have the pthread, okay, anything related to thread, we are using a common header file called common.c, okay, in all these programs. And that is the reason I'm using this option, linker option called pthread with all these programs, even though they are not even related to thread, this particular thing. Okay, and now if I do this IO, that's it, it just prints wrote 12 bytes. Hello world with that space in between and with the \n in between constitutes like 12 bytes. We just wrote those 12 bytes. If you want, you can see the contents of the file. I just did a cat. Cat just shows the contents of this particular file. It just shows us hello world. That's it. And this is what we are going to discuss in much more detail in the third part of the course. Okay. Okay. Okay, so this is just like the introduction to operating system. Like we just saw like the what at a very high level with very simple examples. We just saw like what are the three. Actually, there are four in the sense because the first part has two things. Okay, virtualization has two things. We're going to learn about CPU virtualization and memory virtualization. That constitutes the first part. Second is about the concurrency, and third is about the persistence. Now let's start with the first part. So we are going to start with CPU virtualization. Okay. We are going to have it at a very high level. Don't worry because it's like the end of the class. I think you may be slightly tired. So okay, the first important thing that the operating system does, okay, to virtualize the CPU is it creates an abstraction of all the programs that are running on the machine, okay. So if, let's assume at a particular point in time, if there are 3 programs that are running, as we just spoke previously, like a word processor, a terminal, and like a Google Chrome web browser, then it creates an abstraction called a process, which we actually already discussed, okay.
Can you switch the thing?
So the operating system creates an abstraction called process, and process is the first and the most important, or like the basic abstraction that the operating system creates for each and every running program, okay. A process is nothing but a program in execution. So when a program is executing, okay, let's first talk about like a file, let's say .a.c, okay. We have a file called a.c. We write the C file and we store the C file. Currently, where is the C file stored? In which hardware device is the C file stored? It is stored in the hard disk, right? The C file is actually on the hard disk. Once we write this, it is actually just present on the hard disk. And then let's assume you compile this, okay? You do a GCC and stuff, and you compile it. Let's say -o a and stuff like this, okay? Like a.c. Now you get the executable called a. A is the executable. Where is this executable stored? On the disk again, great. It is also stored on the disk. Okay, executable is also on the disk. And now what you're going to do is, let's assume you're going to run this program by doing /a. When you just do a /a, now what happens? Or what, okay, even before that, this executable that we're talking about, how does this executable look like on disk? Or what are the different parts that this executable has? The important parts, anyone? Can someone?
Header?
Pardon?
Header?
Headers. So header is like a part of the code. Yes, headers are there. You have header files and they are like part of the code. Do you have anything more? Like code is definitely a part of this executable. So if I just draw the structure of this particular executable on the disk, it definitely has like a code in it, okay? It has the instructions that we just wrote in it. Along with that, does it have something more? Pardon? Parameters. Does the executable contain parameters? No. Executable does not contain parameters. We as programmers give parameters to programs when we are executing them. Okay, so it is not stored within the executable. Yeah, so all those things are part of the code section. So those are like, one of the answers was, it may have some binary, okay, to start the program and stuff like that. All those things will be part of this code section, okay. We have something called code. Again, here, even though I write it as code, this is code in binary, okay. This is the code in binary because executable is just like a binary file. Whatever program that we wrote, it is converted to binary and it has the code section in it, okay. Along with that, if you remember, we have something called the global data, right? The global data or the static data in each and every program. And those things would have like a separate part. So other thing is going to be static data. But do you remember whenever we write like an address space or like a memory layout of a particular program, it has code, it has static data, and what are the other two things that it has?
Stack and heap.
Pardon?
Stack and heap.
Stack and heap, okay? But why aren't we even showing that here?
Those are created on execution?
Exactly. So when we have the binary file or the executable, it only has the code and the static data. The other two parts of the program, which are the heap and the stack, are only created when the program is actually executing or running in the memory.
What would the static data be? What is an example?
So static data would be like if you have like a global variable, let's say int g equals 0, that value of g will be there in the static data. So now when we run this, what is happening? When you just run this, we had that executable here, okay? This executable A here. Now this A will be, when we run this, it will be just, if this is the memory of the program, okay? If this is the memory, it is just being loaded, okay? This process of taking the executable from the disk and copying it to the memory to make it run is called loading. We just load the executable from the disk to the memory, and now at this time, if you enlarge this, okay, now let's just enlarge this. If we just enlarge how this program process or this A looks like, now it looks like slightly differently. It has the code part as we have here. It also has like the static data part, and it all has two more things called the heap and the stack. And usually the heap goes upwards and the stack goes downwards. We assume that we start at 0 and we have like the max value here. So the heap is here and it goes upwards, and the stack is here and it just goes downwards. This is how your program, this is the answer for the first or the question number 10 or something like that you had in that intro worksheet, okay? Just this is how a C program looks while it is executing in memory. And this is how a C program looks while it is, not a C program, executable looks while it is actually on the disk. Okay? Any questions about this?
So, can you explain the max versus 0 on the right hand side? Is that 0 address? I think we've seen it previously, 0 address was at the top.
Yeah, so the thing here is like the reason why I am writing 0 here is like I'm just saying like I'm treating the address space like starting from here 0, then 1 byte 0, byte 1, byte 2, byte 3, and maximum, let's say if this address space has, let's say 16 bytes, then max is going to be 15 in this case, okay? And you can actually draw it any way. You can draw it like from upside down, like from 0 to thing, but in this course, okay, to just maintain some convention, to follow some conventions, I think I am used to this. That's the reason I think I am going to follow this. But I think the book uses a different way, but you can use any way. In exams or in anything, you can actually, if you just mark those things clearly, it's enough. Okay? But one thing to remember is that usually code starts at the lowest address. Okay? And then the static data starts. And then the heap starts. And then you have the stack. So if you have like, go and if you take the address of a local variable, okay, inside a function, it is going to be somewhere here. It is going to be somewhere on the top, on the stack. It is going to have like an address, a large address, a huge address. If you take the address of some variable on the heap, if you allocate like a space for an integer on the heap, and then if you try to get the address of that particular integer on the heap, it's going to be like a low value because it is like right here, okay, near the start of. And all these addresses that we're talking about, the 0 to max, are just virtual addresses. They are just virtual addresses. All processes just have some addresses from 0 to some max. Any questions? Any other questions? Great. Then how do we, how do we define a particular process? Okay, a process, when it is executing, okay, it looks like this, okay, and actually a process has its own mission state. And what do we mean by a mission state? One is, we already just saw this, okay, one is definitely the memory. It has its own memory, right? It has its own code, it has its own data, it has its own stack and heap. And we call this in operating systems hereafter, most probably we'll be like using the term called address space. Okay, this is the address space of this particular process. The memory that a process uses is called its address space, or these are the different addresses that this process can access basically. Okay, that's called an address space. And the next thing that So each process has its own mission state, and what we are trying to do right now is trying to see what are the things that constitutes the mission state, okay? One is definitely the memory, and what are the other things? What are the things?
Registers?
Exactly, the registers. Each and every process is going to use the same set of registers on the computer, and so let's assume if process 1 is currently running, it may be having a list of values in all the registers, and when process 2 is going to run, process 1 needs to save its values, okay, somewhere, and then process 2's register values will be loaded in the actual physical registers, right? And so the registers also form a part of the mission state. And what are the different registers that you guys are aware about?
EAX, EBX.
Pardon? Yeah, EAX, EBX, ECX, EDX, then something EDX, then ESI, source index, then destination index, right? All these things are called general purpose registers, okay? General purpose registers. And do you guys know any special purpose registers?
Stack pointer.
Exactly, the ESP is a special purpose register. It's used as a stack pointer. And any other special purpose register? EBP, what does it stand for?
Base pointer.
The base pointer. And what is it used for? It is used for, like, how do we make sure that when a function call happens, we need to switch the, there will be like a lot of details in that, but it's basically to make sure that in which stack we are currently in. It stores the base of the current stack, okay? And then any other special purpose register? Exactly, it's EIP. Yeah, EIP just stands for instruction pointer. And what does the instruction pointer contain? Exactly, it contains the address of the current or the next instruction to be executed, and it depends on the architecture. In some architectures, it just contains the instruction of the current instruction, that is address of the current instruction that is being executed. In some other architectures, it just contains the address of the next instruction that is going to be executed. Okay? And what are the other things that form part of the mission state are the list of files that this process has opened. So each and every process can open its own set of files, right? And so all the files that this particular process has opened on the disk also is a part of the mission state. Okay? So each process has its own mission state.
What about like the cache?
Pardon?
The cache?
So the cache, it's a good question. Cache, does it form, is it a part of the mission state? It's the question. Can someone answer that?
It just gets overwritten by everything.
Exactly. So cache is not part of the mission state because it is just like a common resource that is being shared by all the processes. The operating system just makes sure how to handle the particular cache. It's just like, for example, you really don't need to worry about what are the things that you have stored in your cache because the operating system takes care about that.
Okay.
So these are the things that form part of the mission state. Yeah.
I thought registers were like shared, so how could it be part of the machine state just into a process?
Yeah, that's a very good question. Okay, the question is, the student just asked, okay, I just thought like the registers are shared between different processes. If they are shared, then how can they be part of the mission state? Can someone answer that? Exactly. So the operating system makes own copies for each and every process. So for simplicity, okay, a simple example, let's assume process 1, okay, is currently running. For process 1, it has like a data structure. For process 1, it has a data structure. Let's say it knows now the value of EAX for this process is this, the value of EBX for this process is this. It goes on, let's say value of ESP for this process is this, okay? This is just a copy that the operating system makes, but the actual physical registers are just one. They are shared by all the processes. Does that answer your question?
Yeah.
And in a similar way, we'll have a different data structure for process 2. it will have the copies of its own thing, EAX up till ESP or something like this. Make sense? And this data structure that we are talking about right now, okay, this is like a very important distinction. The actual physical register, okay, this is the physical register on the machine, okay, there is just one EAX register on the machine. But each and every, the operating system has a copy of all the registers for a particular process, and it does that for all the processes on that particular machine. And in this case, we have two processes, it has like two such copies. And this data structure that the operating system uses to contain, to store the machine state, okay, it not only stores the registers, it also stores like a lot more details like the list of open files, okay, and some details about like the address space of the process, okay. All these things are stored here, plus let's assume memory, okay, the details about the memory which form part of the machine state, plus the details about the files are all here in this data structure.
Flag for like it's active and not active, or suspended or waiting,
Yeah.
or is that just somewhere else?
Yeah, we will have those things also here. Yeah, it's called the state exactly. So we'll talk about that, but just here, okay, all these things that we have in this data structure is called the PCB. This is PCB for process 1. This is PCB for process 2. And PCB just stands for process control block. PCB just stands for process control block. This is the basic data structure that operating system uses to store the details about a particular process. And inside Linux or inside x86, if you just think about this is nothing but a struct. And it's nothing but a C struct called proc with a lot of details in it. It will be just like this. The actual implementation will be like this. Yeah. Just a moment, I'm not able to hear you, yeah. Yeah. Definitely, yeah. So it will be like architecture specific, yes. So this here we are talking about like one operating system and one architecture in specific. The same operating system, if we are talking about like, let's say, multiple different architectures, then it can't just use the same proc structure because it may have a totally different set of registers and stuff like that. Here we are only talking about Linux on x86. Any other questions? Okay. So each and every process, okay, can exist in one of primarily can exist in one of these three states, okay. So whenever a process is executing, okay, it is said to be in a state called running. It is in the running state, okay. So when you actually start a particular process, let's say you run or start a particular process, immediately it goes to the running state. Okay, and once, let's assume it is in the running, if it is descheduled, by descheduling here we mean the operating system decides to stop that particular process and run a different process on that machine, okay. So in that case, when it is descheduled, it is said to be in a state called ready state, which means that it is actually ready to run, but just the operating system has made a decision to pause this process for some time so that it can schedule some other process and then maybe come back to it after some time. And this process, this thing happening is called descheduling, okay? Descheduling. And if that process is chosen to be the next process to run, then it means that it comes back to the running state, and this is called scheduled. This process is actually scheduled right now, so it moves back from the ready to the running state. And while a process is running, if it executes some I/O, okay? By that we mean if it tries to read from a file, or if it tries to write to a file, then that is like a very slow operation. Okay, if we just keep that processor occupying the CPU and do that read or write, then all other processes that are running on that machine are going to suffer, because this is like the reading or writing to files to I/O devices like hard disk drives is like a very, very, very slow operation when compared to reading or writing from memory. Okay, and in that case, what will happen is, whenever a process initiates an I/O, let's assume this process, if it initiates an I/O, then it immediately moves to a state called blocked. This process is set to a state called blocked, which means it cannot run until that I/O completes. For example, if that I/O is like getting some input from the user, okay, just assume if your process is trying to get an input from the user, and if it still occupies the CPU, it is waste. And if the user just like went for a break or something like that, then just think that your process is going to run, blocking all the other processes from running, and it is like a waste of the CPU resource, right? And so we will make the process to be the blocked state so that other processes that are ready to run will be scheduled, okay? And once the I/O completes, when the I/O completes, when the user enters the input, or if the read or write completes, then again, sorry, I don't think like it moves here, okay? Once again, you can't just move directly to the running state. This is wrong. Once that I/O is complete, that process will be moved back to the ready state. Okay, it says like it is now ready to be scheduled, ready to run, basically. It is ready to run. So when the I/O completes, it moves back to the ready state. And then now the operating system can decide, okay, now this process is ready to run, I can schedule it. Okay, I can make this process to run. Any questions about this? Can a process move from the ready state to the blocked state? This was one of the exam questions on the first midterm that we had in the summer. Can a process move from the ready state to the blocked state? Yes or no? If yes, why? If no, why not? Anyone? Exactly. So it cannot move from, a process cannot move from the ready state to a block state, because in ready state the process is actually not running, and only a process can initiate an I/O only if it runs, and it can only run only when it is in the running state. Sense? Great. Can a process move from the block state to the running state directly? Why? Pardon? Okay, the answer was we just crossed that arrow, so it's definitely not possible. So the answer is actually it is possible. Okay, it is possible to happen, because it just depends on the operating system implementation. Most of the operating systems don't allow a process to just move from the block state to the running state, but somehow if you are implementing operating system, you may decide whenever an I/O gets completed, that is the next process that is going to be scheduled. If that is the case, okay, then you can move directly from the block state to the running state. Does it make sense? It just depends in this case. But in most of the operating systems, they don't do that, because that decision needs to come from a specific component of the operating system called the CPU scheduler. And that is the reason we move the process back to the ready state, and then the scheduler decides which process to schedule next. Okay? Great. I think the concepts, is there any questions about this, like what we just discussed? Okay, one of the questions during the break was like, is there any specific reason why this particular course is like a 4-credit course, okay, when compared to 354 or something like that? And one of the answers is like, based on my previous experience of teaching this course, this is the first time I have literally seen people cry. Like, cry in the sense like during the course, or like have like people emailing me saying like they have like panic attacks. I'm not trying to frighten you guys, okay? But this course gets into like much more detail, but at the end, almost everyone, so we started at nearly 65, we had 65 students in the summer, and we ended up with 56 students. 9 of them dropped the course, like some point during the course. But all those 56 students, the reviews that we got, the feedback that we got at the end, most of them was like, it was definitely so difficult, and that too, they learned the same course in a span of 8 weeks, okay? Span of 8 weeks. And most of the feedback was like, it was definitely so difficult, but it was worth it to know like this level of detail. Now when I look at, when I just open a terminal right now, the way I look at it is totally different. Because here in this course, as a second project, you will be writing your own shell or a terminal, basically, okay? And so, again, just don't come to any conclusions about the difficulty of the projects just based on the first project. Second project really will let you know how this course is going to be. And again, I'm not trying to like frighten you, but just be prepared. That's the thing. Be prepared for like a great semester is what I'm trying to say. And any other? You guys have any other questions about the course? We have like 2 more minutes. Yeah.
Will the worksheets be posted online, or do we have to get them like here?
Yeah, so the worksheets will be posted online. It will be posted on the course webpage. You may download them, take a print of it, and then you may write it on in paper and just submit it here in class next week.
Can we turn it individually ever, or?
No. So we really don't want to have it like digitally because